Okay, now let's prove another theorem. Assume that the integral from a to t of fs phi s dbs is the limit as mesh of the partition goes to 0 and the summation I from 1 to n of f s at the left end point and then at the right end point and the Brownian motion increment. The definition of this integral is the limit in probability exists. But for this theorem, we assume a stronger condition. Assume that this limit is in L2. Then the stochastic process x sub t, the integral, the stochastic process, there are two of them. One is the integral from a to t. And this conversion L2 is for all t. And y sub t is the integral from t to b f s phi s dbs. Near martingales. Our filtration is the one given by the Brownian motion, which is understood, so I don't write it up. Okay, here this is the proof. First, we prove that x sub t is a near martingale. So we need to show that the condition expectation of x sub t given f sub s equals to condition expectation of x sub s given f sub s. We need to prove this. In order to show that xt is a near martingale, to prove that y sub t parenthesis is a near martingale, we do that later on. So first we prove this. All equivalently the condition expectation of x sub t minus x sub s given f sub s equal to 0. Just to bring the right hand side to the left hand side. Now, x from this equality, xt minus s is this. Now, note that x sub t minus x sub s is the integral from s to t of f. And since I use s and t, so I better use u here, dbu. And that equals to the limit as the mass goes to 0 of the summation I from 1 to n. Of f of u sub I minus 1, phi u sub I at the Brownian motion increment. We go to the next page. I'm adjusting the position. Okay, so this is page 41. Now, for, okay, here it looks like, okay. For each I, we have. Now you will see that we are going to take many condition expectation. For each I, the condition expectation of f u sub I minus 1, phi of u sub I, and the Brownian motion increment given f sub s. This equals to what? So you see here we have something like this. S, t, and here we have u sub I minus 1, u sub I. So we are going to take the condition expectation of this product with respect to f sub s. And we are going to use property of condition expectation. So this part here, I put da. First, we take the condition expectation of given something. This is for in our choice, and then given f sub s. I put this parenthesis up to here. We have the freedom to choose any sigma field here for anything greater than s. This is s, this s. And so first we choose this in order to bring something out. So I put here f sub u minus u sub I. in that case, we can bring this, out. And we can also bring the Brownian motion increment out, because the Brownian motion increment is over here, which is measurable up to here, and this f sub is adapted is measurable up to here, and so it's automatically measurable with respect to this. And so we can bring two things out. Bring f u sub I minus 1 out, and the Brownian motion increment u sub I out. And then the conditional expectation of the only thing left out is phi u sub I. And given f sub u sub I. So this is only thing that we need to take the conditional expectation. So we bring these two factors out, this one and this one out. And then given f sub s. Okay, that is. So that is now, because phi of u sub I is independent of this, instantly independent. So we can, this is the ordinary expectation, and this is ordinary expectation of phi u sub I. Okay, I put parentheses, that's okay. Yeah. So we can bring this, is a constant, bring it out. It's conditional expectation of phi u sub I. And then conditional expectation of f u sub I minus 1, Brownian motion increment u sub I, given f sub s. Wait a second. Yeah. Oh, I think, let's see. I messed up something here. F or this out. Okay, that's fine. Okay. That looks fine. Okay. Now, this is an ordinary expectation of u sub I. Now, what is this conditional expectation? If u sub I is here, that is that. And we do one more time. This is the conditional expectation of f u sub I minus 1, Brownian motion increment, and then something that we can choose. This, and then f sub s. Now, what can we choose for this? We can choose anything greater than s. And so we choose f sub, and of course we want to be able to pull out something. Brownian motion increment is over here and f at the left hand side. So we choose this time is u sub I minus 1. You see the first time here is f of u sub I, and this u sub I minus 1. And so that equals to the condition is the ordinary expectation. And now we can bring this out. Condition expectation of here f u sub I minus 1. Bring this out. Once we bring this out, then we have the condition expectation of the Brownian motion increment with respect to f sub u I minus 1. And then f sub s. Okay. Now note that this Brownian motion increment is over here and given this, and so you see this independent of the sigma field there, and therefore it is the ordinary expectation which is 0, and so this equals to 0. Then we pass to the limit to show that x sub t is a near martingale. Finally, note that y sub t is nothing but the integral from a to b of f s phi s dbs minus the integral from a to t of fs phi s dbs. And now this is a near martingale. This is just a random variable, so it is also a near martingale by our theorem 2 above. Note that. So y sub t is a near martingale. Okay, this is enough for this video. It's a little bit too long. Okay, bye.